Hey everyone, it's me, Bill Younger again. I'm just here to solve some more problems. This time I'm solving a omega as a function of time problem where we're given an omega, which is the angular velocity, as a function of time, and we're asked specific questions. This is basically consistent with Chapter 10 and should be much like some of the examples given in Chapter 10 of Giancolli's fifth edition. So, anyways, let's go ahead and get started by sharing my iPad screen with you. All right, so you now are able to see my iPad screen. It says a merry-go-round has a 4.00 meter radius and its angular velocity omega is omega equals 2.00 plus 3.00 t, and all that parentheticals, once you compute everything, has units of radians per second. That's just the way you can write it. Part A, if t is in seconds, what must be the units of the 2.00 and the 3.00 in the omega function? Part B, at t equals 2.00 seconds, what is the angular acceleration of the merry-go-round? C, also at t equals 2.00 seconds, what is the magnitude of the tangential velocity and the two acceleration components of a point on the outer edge of the merry-go-round? So that's our problem. Let's go ahead and start by writing out solution. So the solution is going to require some basic knowledge. We already know, for instance, that r, the radius, is equal to 4.00 meters. We also know that we're wanting to evaluate various things at t equals 2.00 seconds. And we know that omega as a function of time is equal to 2.00 plus 3.00 t, and all that is in radians per second. Uh, what we're asked in part A is the units of 2.00 is equal to question mark, and the units of 3.00 is equal to question mark. In part B, we're asked what is the angular acceleration. So what we're specifically talking about is the quantity alpha at t equals 2.00 seconds. And C, we are actually asked at, actually I could write that at a lot better than that. That turned out really horribly. At t equal 2.00 seconds, we want to know the magnitude of the angular velocity, or excuse me, the average magnitude of the tangential or linear velocity, which I'll just call v. We also want to know a, the tangential acceleration at that time, and we want to know a, the radial, what we had previously called a sub c, but now in this chapter of the book we're calling it a sub r, the radial acceleration. So that's what we're looking for, and that's what we're going to use. However, I should mention that from S equals R, oops, I don't know what happened there. Let's just undo that. Okay. So I do know that from S equals R times theta, you can take the derivative of both sides with respect to time, and assuming you're going in a circular path, then the R will be a constant, so that you end up getting ds over dt is equal to R times d theta over dt. But we already know, of course, that d theta over dt is omega, and ds over dt is actually our tangential velocity. So we were going to use vtan is equal to r times omega. Additionally, we can take the derivative again, and this time we'll get dv tan over dt is equal to r times d omega over dt. But dv tan, of course, is a tangential, and that gives us that it's equal to r times d omega over dt, which is actually alpha. So that's what we're actually looking for here. We should be able to use all this to figure out what's going on. So let's go ahead and get started with part A. Part A, where I'm just asking you what the units of the 2.00 are. What we see is 2.00 uh, times radians per second is supposed to be the units of omega. So the 2.00 radians, oh, and I should say multiplied, not added. It looked like I think I meant to write an X there and I write a plus. But anyways, the 2.00 according to the drawing is being multiplied by radians per second according to not the drawing. I don't know why I said drawing. According to the equation omega equals 2.0 plus 3.00 t in parentheses. That forces that. We know that the units of omega are generally radians per second as well. That means the units of 2.00 are none. It doesn't have any units. It's a pure number. Now the unit for 3 is 3.00 units times the units for t, excuse me, times radians per second as they are outside the parentheses. All of that should be equal to the units of omega again, which is radians per second. So you can see that the radians per second sort of cancels out of both sides of the equation, and you then can say the units of the 3.00 must be equal to the units of uh oh, actually, since we've now gotten rid of the unit on the right, it's just a pure number, but I have to divide it by t, so this is 1 divided by the units of t. Well, the units of t are seconds, so this is 1 over seconds. So evidently the 3.00 that's in front of the t has to have units of reciprocal seconds in order to make the equation consistent with units. So that gives it to us. I'll write it more succinctly here. 3.00's units are seconds to the negative 1 power, and the 2.00 units are null. I shouldn't say no, but anyways, it's just none. Anyways, let's go ahead and box that off. Now we're going to do part B. In part B, they want to know specifically what alpha is at t equal 2 seconds. Well, what we know is that alpha is equal to d omega over dt. I completely wrote the b, but never wrote the alpha. Alpha is equal to d omega over dt, which we can see is d by dt of 2.00 plus 3.00 t in radians per second. And radians per second, in fact, in general, units are basically just being multiplied by whatever's to the left of them. So you can see all this as a big multiplication problem. Uh, Obviously, in that sense, the radian per second is acting like a constant. So that's one thing to think about. If you actually distributed that radian per second, what you'd get is us trying to take the derivative of 2.00 radians per second for the first term, and that's 0. So the derivative for that part is going to be equal to 0. But we also have 3.00 t radians per second. So the derivative of 3.00 t with respect to time is just 3.00. And since it's already multiplied by radians per second, we're just going to say plus 3.00 uh, radians per second is being multiplied by that. And of course, we already know that the unit of the 3 was reciprocal seconds. So we can now say that the acceleration at any time is actually 3.00 radians per second every second. And that's alpha at t equal 2.0 seconds, but it also happens to turn out to be alpha at pretty much all times that the equation is valid. So I should stress that here, hence I said it. So that's part B. Part C, we want to know again at 2 seconds what's the magnitude of the tangential velocity, and we also want to know what is the magnitude of the acceleration component. So what we're asked for in part C is going to be, for starters, v tangent is equal to r times omega. Well, we just know exactly what omega is, so we can say V tan is going to be equal to 4.00 meters. That's because of the factor R that you see right there. And then the omega is 2.00. This is at 2.00 seconds. Okay, so it's 2.00 seconds plus 3.00 t. Well, actually, I'll go ahead and plug in the t. It is supposed to be a t there, but I'm going to go ahead and write it as 2.00 seconds. Close parentheses, close bracket. I'm turning that parenthesis into a bracket. And then times the units that we had outside of its radians per second. So what you see is the 3 times the 2 gives us 6.00. We add that to the 2 again, that gives us 8.00. And then we multiply 8.00 times 4.00. Both of those have 3 sig figs, so it should only come out in 3 sig figs. And as I said, 8.00 times 4.00 would be 32.0, and that comes out in what you might notice now is meters times radians per second. Notice the 3 had units of reciprocal seconds that you see. Hold on a second. That you see. Sorry, I'm having some technical difficulties getting my laser pointer. You can see this right here had units of 1/seconds, and when it's multiplied by this, it has which has units of seconds. Then seconds times 1/seconds gives you no units, so the 2 times 3 has no units, just like the 2.00 has no units. So 6 plus the 2.00 gives us 8.00, and this all turns out to just be meters per second as the unit. So we can say V. There it goes again. We can say V at, or let's call it V tan, just because that's sort of the wording I want you to learn. V tan at 2.00 seconds is equal to 32.000 meters per second. I'm going to box that off, so you'll recognize it as one of the final answers. And now we have to do the components, the 2 acceleration components. So the 2 acceleration components are A tangent, there we go, starting off with my purple again, is A tangent, which we've already learned is equal to R times alpha. So once we have alpha, we can use that, and that's what part B was about. We were asked to calculate alpha at 3 seconds. So we can now put in 4.00 meters times alpha, which we found was 3.00 radians per second. And this gives me 4 times 3 is 12. Remember, the 3 actually has, in some sense, radians per second on it, radians per second on it, as a result of the reciprocal the reciprocal second that's part of 3.00 and the radian per second that we're multiplying it by. So this should all give you 12.0, carrying 2 extra non-significant digits, again, just for safety. This all turns out to be 12.0 meters per second every second is equal to A tangent. So again, I'll use my purple box and box that off. Now there's also a radial component of the acceleration, what we call the centripetal acceleration, and that radial component can be written as R omega squared, or what we normally used, had mostly used, was v squared over r, which if you put in v equals r omega in that v squared, you'll get r squared omega squared over r, which gives you exactly the same expression. So you can choose to use either one. In this case, since we have the omega worked out, I'll go ahead and just use the first case. So I'm going to write 4.00 meters as the radius, and then omega, which is specifically the omega at t equals 2 seconds. So this should be plugging in my equation for omega. That's 2.00 with no units. Let's make a square bracket here. Plus 3.00 seconds to the negative 1 power times 2.00 seconds, which is chi, and then all of that, of course, is times radians per second. So in this case, I get 3 times 2 is 6. 6 plus 2 is 8. So I've got 8.00, and then all I have to do is multiply or excuse me, I have to square all this. So let's do this. I'm going to put a higher level bracket right here. And that bracket is going to have everything in it squared. So when I take 3 times 2, I get the units canceling out, but it gives me 6.00 with no units plus 2.00 with no units. So that's 8.00 with no units times radians per second. So 8 radians per second squared is 64. And then 64 times 4 is going to be what? 4 times 60 is 240, and then 4 times 4 is 16, so it's going to be 256. So we're going to say the acceleration here is, uh, dang, I already forgot what I said. It's going to be 246 or 256. 0.00, and that is in units of, notice the radian, which is not a true unit, it's actually a pure number, but we do have, as a result of the squaring, we have radians squared per second squared, which again, I'm going to erase the radians, and then it's times meters, so this ultimate result is just meters per second every second. And that's our radial component of acceleration. So I'll say A sub R is equal to 256.00 meters per second every second. And that's our two components. And in fact, you could actually plot them and look at it like this. You would say the tangential component is about 12. So a tangential component might be along an arc of a circle, of course. So maybe I draw an arc of a circle like this. And what we're saying is right here, we have a vector acceleration, which is A tan equals, what did we find that was? 3.00, no, 12.00. And that, of course, is in meters per second per second. Don't have the room for it, but we also have another one that's much larger. This one is A sub R is equal to 256.00 meters per second per second. So those are the two components. That's actually the way they look. And in fact, if you wanted to find the angle downward that the sum of the two vectors are, you could just take and do the inverse tangent. So I'm going to type in tangent inverse of the AR, which is 256, divided by the A sub tan, which is 12. And that gives me 87.3 degrees. So we might say this vector, if we're looking at it like this, we would say this might be our x-axis, this might be our y-axis, and our acceleration vector, I'm going to draw in purple, is like this, with this angle being, by the way, this is atotal, and this angle is about 87.3 degrees. So hopefully that's enough for you to have some understanding of what we're talking about. The big thing here is you guys got to get used to knowing what they're asking for. For instance, when they say the linear velocity or the tangential velocity, or when they say the linear acceleration or the tangential acceleration or the angular acceleration or the radial acceleration, all those terms, you just need to understand what they are. The problems in actually solving them is not that bad. So hope that helps, and you folks have a good day.